Test is on. It's test 8. Okay? And it's on sections 14.2, 14.4. That was ones we did together. We did 15.1. Then 15.2 and 15.3 we did together. And then 17.1. Okay? We grouped some of them in your notes. So you'll see 4 note documents for this test.
Wasn't 14.4 the last one?
14.1 was on the last one.
Oh.
Okay, 14.1 was on the last one. Give me like 3 seconds to ask you first. Are there specific things that you've been wondering? Maybe after doing your problem set, or specific questions you've had?
Yes.
On any of this stuff, Reese?
Is it like a little thing about like specular and diffuse reflections, right?
Everybody's been asking that. Here's what you should know.
Yeah.
Okay.
Because like everything like
It's
when you look really
ambiguous.
close.
Yeah, I'm not going to ask you, is this surface specular? Is this, if it is, it'd be like a mirror is an example of something specular. You know that. There's no question about it. A mirror is specular because you can see your reflection, right? Concrete sidewalk is diffuse. There's clearly ridges in it. It's obvious. It would be so obvious. It wouldn't be something like a rippling river, or there was one that was like the mercury in a thermometer. It's ambiguous because, like, sure, it's metallic, so you would think of it as specular. It's probably really smooth, but at the same time, it might not be smooth if there's a current in it. I mean, there's like, Yeah. So it would be very, very specific.
I'm a little confused, like when you pick Ni and R, like how do you know which one's which?
All right. So Ni, jot this down.
Isn't the first one in the column?
Ni is the first one that the wave starts in, and R is what the wave is going into. And there's a bit of a kink along the way for total internal reflection. That's where it is, and I'll explain that in a minute. But generally speaking, Ni is your starting or your incident wave, the first medium that you're in. And R is the refracted wave, the second medium that you are in. Okay? So going from toward another. It's like initial and final, but it's I and R, not I and F. Okay?
Last night on the problem set, there was a problem that I was like find which one has like the smaller like critical angle or something like that, and I was having trouble telling the Ni and NR, but it wasn't like easy to tell because it wasn't like something going into something.
All right, so let me give you the rule then. Like, that's a good point. Ready? Here we go. Find the critical angle. You don't have to do it, but think about it. Find the critical angle between water and air.
Water.
Which is slower, water or air? Slower moving in water. So water is Ni. It's starting in the slower, always, always, always. And let's explain why that is, Mike. So Snell's law tells us if a ray goes from a fast medium like air, so this is different, from a fast medium to a slow one, it bends toward the normal. So imagine this is air and this is water. If it goes from air, here's the normal. If it goes from air at an angle of, say, 30 degrees, then it will come out in water at an angle that is less than 30 degrees. This will be your theta, and it's got to be less than 30. Again, when it goes from a faster moving to a slower moving, it slows down the wave. It literally slows it down, which causes the wavefront to get backed up. So instead of going like this, they slow down and they kind of curve like this. And it's not a perfect line, really, but we're saying it is. Okay, that was that idea. Now, for total internal reflection to occur, which is where you find the critical angle, you need to go from slow to fast. Always, always, always. Because, remember, from slow to fast, it bends away from the normal. And here's what it would look like. I'm going to redraw the same diagram now, but I'm going to draw it with H2O here again and air here, but the wave is going to be going the opposite direction. Here's the wave now. Here's the normal. And if you remember, here's the ray that's going to come out. And it's going to get bent away from the normal. So say this was 45. This might be something like 70, right? When that angle becomes greater than 90 instead of 70, what happens? Take a look at my arm. Watch. So here's 45. If it were passing into the same medium. But since it's going into a faster medium like air, it speeds up. So it bends away from the normal. If it speeds up so much, it would actually bend back into the medium. That's total internal reflection. That's what's happening there. So as this angle increases, say this angle is like 50 degrees now. Now coming in at 50, or say 70, make it even higher. Now look at this. I'm coming in at 70. This is going to bend a lot. It'll bend back in. So if you can find the critical angle between water and air, and your angle exceeds that, so let's say, we could do it. Air is 1, and we know that the critical angle,
You're going to get the table, right?
yes, you'll have the end values written, but you should know air. I mean, I'll give it to you, but you should know it, right? Just hypothetically, you should know it, but you will be given it. But by the time you've done all these labs, it's like, so sine inverse of, and it's always going to be the smaller index over the larger, if you ever forget. Air is the smaller one, right? And it's starting in water. So water is going to be down here, and air is going to be up here. So it's going to be 1 over 1.3. And it's 1.333, right? What do you get for this? Can somebody give me an actual angle? What do you get for the sine inverse?
Is this a problem with both processes?
I think this was one of the ones of the problems that you found the angle for, yeah. 1 over 1.33333. Sine inverse of that.
48.6.
48.6.
Yeah.
Check others, please.
Yeah.
I believe you, but just so we all know we can do it. 48.6. Now, you got do 1.333. Put a bunch of 3s because it's really 1.3 repeating actually, or close to that.
So 3 3s, right?
I think it's 3 3s it gives you, whatever it was. But so around 50, 48.6. You said.
Yeah.
All right. Now, here's what this means. Currently, this would not undergo total internal reflection because what's the incoming angle? And that's less than this angle, isn't it? But the minute I make this angle bigger than 48.6, if it's exactly 48.6, the ray will refract all the way to the normal like that. It'll have a refraction angle of 90 degrees. And it'll be along the surface, the light. Anything bigger than the critical angle, 48.7, it will refract back into the medium at some angle. And that angle will then be, this refraction angle will be bigger than 90. But the idea is that it's total internal reflection because in essence, it's not even refracting. It's kind of reflecting back in now, right? Although it is a type of refraction. Because it's a refraction of an angle greater than 90 degrees, causing it to reflect back into the medium.
So wait, it never goes in?
So if the angle exceeds the critical angle, the light ray reflects back into the original medium. It does not transmit through it, which is wild. Because the surface between water and air, there's nothing blocking the light. Think about that. It's as if, imagine you have a flashlight on the bottom of a river or a lake. And the lake is still, and it's in the water. And the light is going into the water, and it wants to escape out to the air, right? The light should be able to come out to the air. There's nothing on the surface blocking it. There's no seaweed, there's no whatever, you know, there's nothing on the surface literally blocking it. So it should transmit because it's a transparent interface. But it doesn't. It reflects back into the water. That's what happens in your fish tank at home. The angle of that light is usually a very high angle like this, so that the angle away from the normal exceeds the critical angle. And what happens is that light ray stays in the fish tank, giving the fish more light, and it doesn't make the fish tank glow as much. Okay, or transmit as much light out.
Wait, so if the
If the,
refracted angle exceeds?
if the incident angle exceeds the critical angle, so hypothetically speaking, let's write 50 degrees here, okay?
Then there's total internal.
Then there's total internal reflection.
It has to be 50 degrees though?
Well, bigger than 48.6. Right? That was the critical angle. The critical angle between air and water is 48.6. So if it were 50 degrees, like the red one I'm showing here, it would come back in. If it were. If it were 60, if it were 70, if it were 80, if it were
I thought you were
48.7.
saying the 45 is now 50.
Well, it's the same ray. I'm just changing the angle, which is coming in now. So I've got a flashlight, and I'm going like this now to increase the angle. Okay? Marianne. Ni is the higher N or the slower, very good, for total internal reflection. And Nr is the faster or the second or the lower N value. Here's what you can remember, folks. Take a look, please. This can never be bigger than this. The numerator right here can never be bigger than the denominator. Try it. You get a domain error on your calculator. The reason is this. I can show you in 2 seconds. A sine curve ranges from 1 to -1 in its range values. You are doing the inverse, right? So you're trying to find, technically speaking, the y value. Or you're trying to find the x value given a y value. Are there any y values bigger than 1?
No.
Are there any less than 1? Not less than -1.
No.
So you cannot put a number in there that's bigger than 1. So when you look at the fraction. Whenever the numerator is smaller than the denominator, divide these. You're going to get a decimal, aren't you? You're going to get a number that's like around here, 0.75. Okay, it will work. Anything, if you have bigger over smaller, you get a number that's bigger than 1. It's going to try and find a value out here on the graph. There's nothing out here. There's nothing out here above and below the graph. That's the reason why. You'll learn more about this in pre-calc. Okay, but just to give you an idea as to why. All right? Other questions? It's a good question. Philip.
For when we're finding NR, do we need to use sine -1 or because like on the lab when I found it I got 2.96. Like I keep like running into problems finding NRs.
Let's do it. Take a look. The only time you will ever use a sine inverse, God bless you, is if you're trying to find the argument of a trig function. Now let me explain what that means. I want you to know the term now. If you're trying to find the argument of a trig function is when you will use the inverse. The argument is whatever theta is here. If this were like sine of x, if you're trying to find x, you will use an inverse. If you're trying to find a variable, you divide by the whole thing, sine theta r on both sides. Right, Phil? That's what you're trying to do?
Yeah.
So divide by the entire thing, sine theta r, and these cancel, giving you nr. And now you have nr. But at this point, you need to plug in your thetas in both spots and do the sine of 30, or whatever it is, times ni, over the sine of 70, okay, or whatever it is.
Yeah.
All right? It's a really good question. Good thing to remember. So when finding n, you don't use the sine inverse. When finding theta, you do. So as far as concerned, polarization, I want you to know the applications of it. Okay? I'm not going to ask you the scientific portion of what happens when light is polarized. But what it does, again, though, just so you know, is it rearranges the angle or the orientation of the EM wave so that all of your magnetic crests and troughs are lined up, and so that all that of your EM waves are lined up. But what I want you to know are the applications. What are some applications of polarized light or polarized glass?
Reduce glare on glasses.
Reduce glare, sunglasses, good. Laptops, your computer screens. Remember we talked about how that's polarized light.
Tinted car windows.
Yeah, tinted windows, like car windows. Some of those are polarized windows now. Good, that's 3 applications. I just want you to know applications. If it's multiple choice, if it's a free response, something like that. Polarization as far as electric charging goes, if you remember, is when you bring a charged insulator, I almost said inductor. So if I were to go like this, and charge this up, and we're to bring it near something, hopefully it might work. Let's see. It's plastic. No. I need like an actual rod. If you charge a rod with a like a glass rod with a piece of like wool or fabric, it'll charge negatively. When you bring that near something like a piece of like paper or something, it'll cause the poles in there to switch. That's why it's called polarization. And it brings all the positive or negative poles to the surface, and the other ones on the other side. You're never touching it though. You're just bringing it near. Polarization, and it causes like a temporary charge on that, causing it to like jump up to it.
And there's nothing lost.
There's no net change in the charge. Yeah, you're not inducing a net charge on it.
Do we need to know that stuff, or?
You should know the operation of each of those. Yeah, how they work. We talked about all of them yesterday.
No, because I'm saying, but obviously, you need to know to understand it, but like on the test, what you're asking, because you said you weren't going to ask about scientific.
Of the light polarization. This is charging by polarization. So charging by contact between 2 insulators, charging by induction between holding an insulator near a conductor and then grounding it with the wire, having the electrons flow out, and then charging by polarization, having an inductor, an insulator, near another insulator, causing the poles to switch. There's 3 methods we went over yesterday. Not going to review those right now. I'll wait till the end if we do, because those are fresh. What are some other stuff?
Wait, why isn't when you rearrange the formula for Snell's law, why don't you, to find theta r or theta I?
You do an inverse for those, yes.
Okay.
Absolutely do.
You don't do that?
You don't do an inverse when you're solving for Ni or Nr. Because there's no trig involved there. You just divide by sine theta, whatever it is.
Okay, yeah.
That's only because you're separating the sine from the angle.
Correct.
Yeah,
You're literally
that's-
taking the angle out of the sine function.
Yeah.
You're extracting it out of a function.
Yeah, that was also my question because I was getting confused as to why sometimes we'll do that.
I would like to quickly talk about something that I didn't mention in class yesterday, and I realized it when I got home. Or actually, I realized it in the other class, and I realized when I got home I wanted to talk about it. So, I talked about insulators and conductors.
Yeah.
Okay? And an insulator is something that doesn't transmit charge. A conductor easily transmits charge. Typical conductors are metal. Now, I mentioned but didn't go into detail about semiconductors and superconductors, and I do want to talk about those. Does anybody know what a semiconductor is and kind of how it works? You don't have to know exactly, but an idea. Nick?
Is it like an LED light? It's like you add like a metallic impurity to something, so it kind of transmits electricity.
Absolutely right, Nick. Very good. And that's the metallic part. An example would be LEDs. So, a semiconductor is this. It's an insulator normally, but sometimes in the presence of some metallic atoms, it becomes a conductor. It's not something that's like it's a conductor or not. It depends on that presence of the metallic atoms. So usually silicon, germanium, those are two things that are added to insulators to make them conductors. Okay, to make them conductors. Now, a superconductor, that was a semiconductor. A superconductor, anybody know that one?
Really just conducting stuff.
Yeah, you're absolutely right. It's really good at conducting stuff. Now, do you know how it becomes really good at conducting stuff?
Metallic ions.
Think about computers. Who knows about computers? How do you make a computer run faster?
Oh, fast. Cool it down, right?
Oh, cool, yeah.
The processor and you cool it down. If you super cool a conductor, specific ones, it becomes almost a perfect conductor of electricity. We haven't studied circuitry, but electricity flows and there is resistance. When electricity flows through a circuit, the resistance, you see a light bulb. The light bulb is a resistor. It's giving off that energy as a resistor. When it travels through your computer, there are resistors in there to slow down the flow or else you'll get a short circuit. Now, if a resistor has such a low temperature, like when you overclock a computer, you get it to run faster than its specifications. It's called overclocking because you run liquid nitrogen over it, which is a very cold temperature. And it cools the processor down to very low temperatures, causing almost zero resistance. So a superconductor is something that at very low temperatures has almost no resistance or negligible resistance.
They do that
Okay?
in the military.
Yeah, for things that have to run in really fast computers or really quick processors, they super cool them. Watson, you know, it was in a refrigerator. He kept saying that. Those are all the fans you were hearing. It was cooling it down.
Wait, so something that at low temperatures?
At low temperatures, acts as if there's no resistance involved at all. It's a perfect conductor of electricity. I really hope, we're going to talk about electricity and stuff, but I really hope at the end of the year we have time to get to heat and thermal stuff, because I love heat. The thermal fluids. We'll talk about fluids. Fluids and heat are really not on your SAT subject test that much, so I don't really include them that much. But I usually get to fluids, I sometimes get to heat. I hope we get to that. Okay? And like thermal management. It's really an interesting topic. So anyway, that's what I wanted to add there. What other stuff do you have to ask? You want me to go over some questions I think might be things you should know?
Yeah.
Maria, go ahead quick and then I'll go.
All of the equations that we have to use are all the...
It's only Snell's law and the critical angle, that's it. The math is very small, it's short. The math might be only 15 or 20 points at most. So those that really bank on the math, it's more conceptual, this one. Just give you a heads up.
Wait, sorry, say that again.
It's very little math in this one. Snell's law, critical angle, that's kind of all I can ask. We haven't done any other math.
What are you?
70-point test. 70-point test, I'd say about 20 points max are math. The other 50 points will be a combination of multiple choice and short answer. Reese.
I don't really understand, I guess I understand, but induction, That's like.
Want to go over it?
Yeah.
Sure.
What's the usage for that?
It's to give a charge to a conductor. To give a charge to a conductor. That's what induction is really used for. If you wanted to charge up something that was metallic or that was, that needed to hold a charge for some reason, in circuitry it's a little bit different. For the sake of what you need to know for this, that's what it is. Let me go over the process. So the process of induction, you bring a charged particle or object, let's say this is negatively charged, near a conductor. The conductor has both positive and negative charges, but the positive charges are here, and the negatives are here because the negatives get pushed away when this rod is brought near it. Then, you ground it next. You attach a wire. You attach a wire to a grounding source. When you do that, the electrons all flow out because they want to get further away from that rod that you see over here. When those electrons then flow out, what you're left with is a net positive charge in this conductor. You remove the grounding source. Okay, you get rid of the grounding. You detach You detach the wire, leaving all positive behind, and they're still pulled over here because this rod is still here. Oh, it's not touching. I should redraw that. It's most definitely not touching. It's an induced charge. Induction means not touching, so I need to emphasize that. Okay, and then when I remove the rod, when I remove it out of the way, it's now gone, and these positive charges now just spread out.
What's the purpose of that?
The purpose is just to charge a conductor. That's all it's for. If you want to charge a conductor, something that conducts electricity. If you want to charge an insulator, you can use charging by...
What would you use that insulator to do?
You would do a lot more than what we're going to do in this class, or for this right now.
So I don't need to know
No, you don't have to know as far as the test goes, but you should know that conductors and insulators and charging things by conduction insulation, a lot of that occurs in circuitry. Okay, there's a lot more in circuitry than that, but a lot of that does happen.
So then if you touch that, you get shocked, right?
Correct. This would now have a net positive charge. If you touch this, it would shock you for sure, because you are both conductors. Your electrons want to flow into there to equalize the charge, so they're going to move, and that's the shock you're going to feel.
What if the negatively charged rod did touch
If it did touch the conductor,
would the electron just go from the rod to the plate?
was it grounded or no?
Well, what if it was or wasn't?
If it was grounded,
Like if there was that line going down from this.
if it was grounded, yes, for sure. If it wasn't, I don't know. I'm wondering. We bring it near it, and induce the charge, we push it away. If you touch, would it transmit that charge? And let me think about it. I don't know. But if it was grounded, it most definitely would. Because the electrons want to flow to a grounding source. Maria?
What are these diagonal lines?
What are the what?
Diagonal lines.
Crossing off the grounding. Sorry, I was just saying, you attach a wire, then you detach the wire after. Mike?
But remember that video you showed us the other day with the guy touched it and nothing happened? It was like...
When it was charged, when he touched it, it did, absolutely. He got shocked.
No, but I'm saying, and then he touched when he touched that thing, but when he touched the big thing, he held his finger on it and did something else, and then the electric waves stopped.
Because what he was doing was just grounding it when he was touching both. Yeah. He was causing it to be in equilibrium in a sense. That's why it stopped bending that pin or that needle.
So that brought the negative charges back or something?
It created a balance in there.
Okay.
It depended on, I forget if there were abundance or deficiency of negative charges. So it would be one or the other, depending on what it was. Other things you should know for the test. Other stuff you should know. Again, 70 points, I just said.
What are you going to ask for primary colors? Just what are the primary colors?
No, I'm not going to probably go into primary colors. I'm going to look at more the colors of physics. So what is the color green that you see? What's really happening?
It's absorbing green.
Yeah, it's reflecting a bunch of light waves that together make green. Okay? That together make green. So not just whatever green is, but there's a combination of it.
So what is green?
Whatever green is. I'm not going to ask you what green is made up of, what colors it's comprised of.
That'd be a
the three colors you should know, right?
Red, green, and yellow.
Red, green, and
Blue.
blue. For light, red, green, and blue. Not for pigments, okay? That's what all the colors are made up of waves.
I don't think TVs didn't they like add yellow though to like something to make it like, and now it's like some sort of big thing. I think there was
Take a look, man. Look it up. Let me know. You should know the difference between specular and diffuse, but not necessarily identifying surfaces that are a bit ambiguous. You should know about electric waves and like the fact that in air they travel faster, and in like something like water they travel slower. But generally speaking, they all travel at the speed of light, right?
What is the air waves? What did you say?
Electromagnetic waves, EM waves.
Yeah, they did.
Wait, why do they travel slower in water? Because in water is really a conductor.
Oh shit.
You're not talking about charge, you're talking about an EM wave. They're different. Electromagnetic waves versus charges. Charges are just electrons flowing. Those want conductors, yeah. So it would go fast. Water's a better conductor than air for sure for electrical charge, okay, but not for EM waves. They're different things. You should know that if there's ever an imbalance of charge, it's the motion of electrons, right, that cause it. So if I were negatively charged, it means that I gained electrons. If I were positively charged, I lost electrons. I don't actually gain protons. That would be crazy. That would mean you'd have... Yeah, the element would change. Your nucleus would go crazy. You can't do that. You have a nuclear reaction. So that's what a neutron bomb, a nuclear bomb and stuff has to do with splitting, the splitting or the fission of a nucleus. Okay?
It says it did add yellow to it, and it changed the amount of colors from the billions to the trillions.
Sure, alright. Cool. That's really cool, Mike. I didn't know that. Yeah, Maria.
Only one TV there.
Folks, guys, stop. Listen.
When it's an imbalance of charge, they are electrons.
When there's an imbalance of charge, it's a result of the electrons moving away or toward.
Sharp.
What do you call it?
No, I actually was. She asked me what the TV company was that added it.
If there is an equal amount of protons and electrons, if there's no charge, it's neutral. Hey, what about the color white and black? What's the difference between the colors white and black? Catherine.
Black absorbs all the colors and white reflects.
Perfect. Black absorbs all the colors, white reflects all the
Wait, by all the
colors.
colors, you mean just like RGB or...
What'd you bet?
Wait,
RGB.
Every wavelength. Every wavelength.
Great.
What is the phenomena of dispersion? And I went over that quickly.
It's all
Goes out.
Yeah, it's all the wavelengths spread out so you see all the colors. So a prism or a rainbow or water droplets are caused by dispersion, right?
Can you watch it over Rainbow?
Maybe, yeah, maybe.
No way.
Oh my god. It's
Converging and diverging lenses. Converging and diverging lenses. Let's draw a person's eye that has farsightedness. The rays hit the eye and they come in too far, right? That's what happens. So we want to converge them sooner, don't we?
Yeah.
So let's put a
Lens.
concave.
Lens.
converging or convex lens, not concave. Put a converging lens that causes these to converge sooner,
But you have to draw that
and then they
certain way.
converge right on the retina. You should know the theory. If you want to draw it, it might help. If it helps you.
No, I'm saying like the lens. Do you have to draw that in a certain way, or does that not matter?
It definitely matters. That's convex or converging. This is diverging or concave. They're very different lenses.
Oh, like that. I'm saying, but like you don't have to draw like specific like. Or never mind.
If you're going to draw it, you should draw it the right way. If you're going to
No, I'm
describe
not
it in
saying,
words, it's
I
fine.
was saying like different, as in like fatter than that, not like because I knew you had to draw that like that and that one similar to that, but. Like,
Okay, this one has to have a curve outward. This has to have a curve inward. So normally for nearsightedness, here's what happens. The rays go into the eye and they focus too near on the person's eye, right?
Yeah.
They focus here too soon. So you can see near, right? For farsighted, you can see far. So we use the diverging lens to cause these rays to diverge, and then they focus a little bit further down the road because they're diverging, they're separate, and they focus right on that retina there. Okay? So you correct farsightedness. So if I can see far and I want to read a book, I use a converging lens at the top. Again, if I can see far, I'm in this case, I use a converging lens at the top so I can then see near. If I can currently see near, which is normally what I can, and I can't see Reese right now, I put my glasses on, which are a diverging lens, which cause my nearsightedness to make it better so that it lands on the retina so I can see far now.
Okay, so let's say that your eyes are...
I am nearsighted. I can see near.
Oh, yeah, sorry.
If your eyes are fine and you wear nearsighted glasses, you become farsighted?
If your eyes are fine and you wear nearsighted glasses, you would become farsighted. Absolutely. Because then you would cause the rays to diverge and focus too far or past the retina, making you farsighted.
Farsighted isn't like, it's not like people like when you give them something, they like put it very far away from you.
Correct. If an old person is farsighted and they can't read this, they go like this. Because they can see far, so they're like, move it away and I can see it. But up close they can't. Which doesn't make any sense to me, theoretically. It's crazy. The other one makes sense. It's like, well, that's really far. I can't see it. Let me wear a magnifying glass or a telescope, you think of.
It's kind of crazy that they figured it out.
Last thing. Guys, we have 3 minutes. One more thing. Fiber optics. Fiber optics. What's the deal?
So, in the tubes
it's at a certain angle. It's at a certain at a certain angle, so they bounce off instead of going out.
Yeah, I heard from have critical. I heard they bounce off as Reese said in the back. They keep bouncing off. It's got to occur. Listen. Ready? Here's the ray. It strikes the surface. Where's the normal? Well, here's the normal. Take a look. Look at that angle. Isn't that a very big angle? So for fiber, let the sirens go by. For fiber optics, by the way, that's the Doppler effect. When you hear the sirens really high pitch, they're really low pitch. We'll mention that later in the year. So the angle that you see here is greater than the critical angle. And this happens a lot because in fiber optics, these light rays are almost parallel to the actual tube itself. Right, here's the tube itself. Here's the tube itself. That's the surface. Well, this is almost parallel. This is a big angle. It's definitely bigger than the critical angle. So this will then bounce. And watch what happens. Now this is the normal right here. And take a look. That's another big angle. So it consistently bounces at very high angles, causing total internal reflection. And therefore, light source over here